Okay. That's it, that's fine.
The microphone is probably, are you using your own computer? Then it's
So this is it, okay,
your computer's mic.
yeah. Okay, that's okay, that's okay. Yeah. Hmm. It's all right. So I think I have to speak somewhere around here, not over there.
Yeah, you sound fine.
Ah, there's something else in here. What is this? Is this a pointer? Maybe it is a pointer. Ah, it is. A pointer. No, no, it's not a pointer. It's supposed to be a pointer.
That's a pointer or like, it's probably, it might be connected to the main computer to advance slides.
I think it is, yeah.
Nice.
They're not gonna let me do it. It's okay. What is this one?
The computer in here probably has, this is a slide advancer.
Bigger screen?
Yeah, this thing is a Logitech slide advancer. So like if you're presenting, oh no, this is a pointer. But it's dead. There's no battery. But let's see. Let me see. Oh, here we go. There we go.
Here you go.
Yep. All
Yeah.
right. So you're
Thank
good.
you very much.
You're
That's
welcome.
great.
Sure. Just when you're done, just make sure you turn the side button off. Yeah.
Side button, this one, okay.
Yeah. And then the red button is your, this thing is your pointer. Push that and it's on.
Yeah.
Okay. It is a pointer. Okay.
It's just information, but- So.
Maybe, Yes, this is. I don't do it anymore.
Okay, we are on time to start our seminar today. Thank you so much, all of you, for coming and joining. Again, big thank you for our sponsors, I-CPIE, Imperi, and Atlas. Today we have, again, the director of Atlas, and today Dr. Rickles will do the introduction of our invited speaker, Dr. Ye, that I deeply appreciate his presence here with us during this week. So,
Yeah, thanks,
Dr.
Mr.
Rickles.
Irving. Yeah, so gives me great pleasure to introduce our honored guest. Came all the way from the West Coast, or did you travel further?
Well, I come from Japan, actually.
Okay, other side of the world. So I heard he's still adapting to the time zone, but anyways, Professor Ye from Oregon State University, since what, 2003?
Yes.
So that's 23 years. So he's a professor there of civil and construction engineering. So the departmental topography is a little bit different than what we have here. Now, as you may gather, his field of expertise is hydrodynamics, in particular tsunami. So he's world renowned for his expertise, and he'll explain probably the various field reconnaissance he's done, but I can name a few of them. They include the 1992 Nicaragua tsunami, Flores, 1992 as well. It was a busy year. 1993 Okashira, 1994 Sukhothai, 96 Peru, 98 Papua New Guinea, 2004 the Great Indian Ocean. I think most of you maybe remember that. And the most recent one is in Japan, Tohoku earthquake of 2011. I don't know if you talk about any of those today, but those all sound very interesting. So he's very involved in education. So he organizes a lot of workshops to answer some questions, but also to train the next generation of workforce. So quite involved in that. He's good at long wave hydrodynamics and modeling, tsunami measurements, bathymetry, topography, seafloor, tsunami data repository, and various simulations with tsunamis. So but the majority of the recent work has been applied mathematics. So very important to be good at math when you do these things, and numerical expectations and expertations. I guess we'll ask you about mitigation strategies. So that's going to be discussed, or that's his background as well as information technology. And so he's done also collaborative experience with Japanese scientists and engineers. I think he's a really good connection for bridging across to our colleagues there in Japan. And to give you some examples, he's been involved with a research program of structural control performance with Shimizu Corporation, as well as with the Public Works Research Institute, University of Tokyo, with laboratory experiments, and collaborative engineering education with Tohoku University. That's close to where the earthquake and tsunami was in 2011. And lastly, mitigation measures with Kyoto University. So with that, I'd like to extend our welcome, and the podium is all yours.
Thank you, James. Thank you for coming 2 days in a row. Yeah, I really appreciate it. I showed this stuff yesterday, and this is the picture from Fukushima. I think it is about 10 months after the event, because in the Fukushima, there was a Fukushima Daiichi nuclear power plant disaster. So this place was totally closed at that time. And this is few kilometers south of the Fukushima Daiichi and very close to the Fukushima Daiichi power plant. Take a look at this. This pole here, let's see, right here. This used to be paved. Of course, this is paved location. So there's something going on that's softening up on the ground surface. So saying that, I'd like to talk about today is
Click on it. Just click on it once.
quick words first?
Get focus.
I don't understand. What is going on? They don't like me.
Just no, left, right.
What did I do?
It's okay. Just you're left, right. You're good now.
Oh, I see. So I want to talk about soil instability related to the tsunami actions. That's what I'm going to do. So my interest of this is started a long time ago. This is a study which I did in Japan about quarter century ago in PWRI in Japan. We did some great experiments using a very large flume. It's 135-meter long, and I think it's about 2-meter wide. And they put this cylinder, 50 centimeter in diameter, and the bottom part is made out of plexiglass. So I can embed it. I can place the miniature video camera. I think actually two or three of those, I think. Yeah? So I can see from inside out. I can see that the soil behavior along the wall of the cylinder. That's what I did. Right? And this is the picture of how I put this on. This is cylinder here. The wave is coming from here to here, making a solitary wave, impinging to this. So what I'm going to show will be this. I'll show you some video after this. So ABC, A is the offshore side, B is the side, C is the inshore side. This is a side view. This is a top view. Okay, I have this kind of funny pictures because this is the montage of the two videos. And this is the inside pictures. This is offshore side, and this is the inshore side. Okay? You understand that? I'll show you the video for this. Let's see. Maybe I can just push this one. Oops. I was not. So I may have to do this way. How do I do? Let's see. Oh, here you go. I have to see this one. Here we go. So it's a line up and draw down. I like you to pay attention in this side, inshore side. of the cylinder. So it's a drawdown. That means rapid reduction of the water surface. It looks like it's liquefied, isn't it? So you can actually see the liquefaction for this. You know, during the drawdown, water surface drops very quickly. While in the pressure in the soil is still there. So that creates some instabilities. So for this, I just try to explain this. In the rapid drawdown, you're gonna have a pressure, oops, to be like that, right? In other words, this pressure is greater than this if you're a rapid drawdown. So you're gonna have moment and liquefactions, right? So that's, you understand this mechanism. If you have a quick withdrawal, the sediment becomes unstable because pressure in the sediment is greater than the outside. Yeah. So this is the way I try to do. Another evidence is this. This is a picture taken in the 1960 Chilean tsunami in Japan. What does it mean? The earthquake source is 17,000 kilometers away. So that means this place doesn't have any ground shaking. Simply you have rapid drawdown, run up and drawdown. That's what you have. So run up in here, drawdown here. The failure on these key walls. So this might be a similar mechanism for this. And this is a picture which I took in 2011. Also, it's at the port. Take a look at this. Something going on. And that's why it is my interest to try to sort of explore what is going on that soil condition for the tsunami loadings. The tsunami loading, maybe I can just next slide. This is a very simple explanation for this. You know, for the geotechnical engineering, you make up if this effective stress becomes close to equal to 0, you're gonna get the momentary liquefactions. Sigma is that the soil stress. Total vertical stress is sigma. And the pressure is this quantity. I have a SOC in here. That's the area for the grain to grain contact. It's going to be very small, but it's not exact. So that's what you have. But what I'm going to try to do try to measure the instability of the soil, I'd like to use this delta. The reason for that is this is the one we measure in the laboratory. If the initial condition is there, I can just zero it. So this is sort of convenient way to handle the data. So if this quantity delta is close to this quantity, then you're going to get the potential liquefactions. But if this quantity is close to this value, still very likely unstable. Right? So I'm going to use this quantity to talk about soil instability. Right? And so another thing which I did previously is this is the criteria for the liquefactions. No, I have to use PPDZ. Because those of you who took you record the fluid mechanics. Pressure by itself is not mean, right, for the fluid mechanics. What is important is a gradient of the pressure. You know, you learn this one. You learn from that the gauge pressure and the absolute pressures. Number is very much different. What is important is difference. So that's why we have this one. That's why we use this one. Now, so question here is, will the soil be stabilized instead during a tsunami run-up? If you have a rapid run-up that creates the pressure gradient going to upward, meaning that the pressure force is acting downward. So it's going to be stabilized for this. That's the questions. Is this the case? So that's the question which I have. And this is the observation which I made in the Onagawa, which I talked about yesterday in the Onagawa. This building, we talked about this building yesterday, is toppled. Okay? And this building has a pile foundations. And this is located inland, somewhat inland. And this is moved about 30 meters inshore. That means this building failed during the run-up, not the drawdown. The topple and going to the inshores. And this is actually the numbers, but so can soil be weakened during the tsunami's run-up, rapid run-up? It doesn't think that way, but maybe it's presence of the impermeable layer will do it, because this place was paved. Right? So if so, to what extent? So I'm going to do laboratory experiments for this during the run-up and drawdown. In order to do this, I'll try to make a realistic scale for this. Oops. Because this is, I think I showed you yesterday also. This is a major run-up and drawdown process in Onagawa. If we're going to try to do laboratory experiments in the hydraulic scale, 1/40 scale for this, then maximum run-up height will be 44 centimeters. And the water pressure is going to be 4.3 kilopascals. Velocity is going to be, by the fluid law, it's going to be 1 meter per second. Now, if you scale that fluid law hydraulic experiments, that's the way we're going to try to do. Yeah, that would be a problem. Problem is that creates some kind of uncertainty for the scale effects. If you calculate the Reynolds number, so in the field, it's 10 to the 7th power. In the laboratory, you're going to get to 10 to the 5th power, 2 orders of the magnitude different. That gives you huge uncertainties. This is only just the fluid flow. I'm not even talking about the condition in the soil. It's going to be a huge problem for this. So, what can we do? Before I'm going to do what I'm going to do is I'm going to just briefly show you scaling. Okay? For the fluid is easy. If you know Navier-Stokes equation, right? Then it is good. You can match it. Once you scale, you're going to scale this quantity order 1, order of the magnitude will be extracted the coefficients. Stockholm number, Euler number, Reynolds number, and the fluid number. Okay, if all those numbers are equal between field and the model, you're gonna have a total similitude. You have to worry about the boundary conditions, but you can still do it. Okay, in the soil, it's not really easy. It's not easy at all. I'm just using a very simple diffusion equations. I don't want to have any complicated stuff because it's so complex that it doesn't work for this case. So I use a Tazagi's diffusion equations. You're going to have a Tazagi number and geotechnical engineering called time factors. Right? According to Tazagi number, it's going to be like this. Okay, K is the intrinsic permeability. This is a time scale, length scale. Viscosity. This is the modulus of the elasticity. This is the porosity. Okay. This is not even exact. This is still lots of hand waving part, right? Because soil is so much complex. But at least you can do this. This matches, then it's going to be perfect similitude. Good part on, well, you can manipulate those stuff, even that the soil medium doesn't change, you can change the viscosity. Now, in the boundary condition is this, fluid soil interface, shield number has to be correct. This is the ratio of the shear stress to body force. So, knowing this, what we try to do is we use a centrifuge. Centrifuge is you can adjust, you can control the body force. I can change the gravitational force. It's not that, using that centripetal force becomes body force. So body force is controlled by that centrifugal force. So that is nice. So if you use that 41 to 40 model, you can use, half the that. You can use 40G kind of stuff, right? And then for this, relatively small scale model can mimic the large scale phenomena. That's what we can do. And you can adjust the Tazagi number because model is small enough. If it's model is not small enough, then I can use viscous fluid. If the model is large, it's not easy to do. Right? And for this case, you can adjust the fluid number low, but still I have problem with the Reynolds number. You're gonna get the mismatch in the Reynolds number, but it's gonna be better if you adjust the gravitations. It's better, but still you have scale effects based upon the Reynolds number. But also, you know that if the Reynolds number is large enough, then probably, let's say, if Reynolds number is large enough, that means inertial force dominates compared to viscous force. So if it's large enough, we can hope it's much as well. That's our hope, okay? That's what we try to do. So for this case, if I use 1 to 40 scale, this is a traditional model, centrifuge model is like this. You're gonna get exactly the same pressure, and that the velocity is exactly the same as the prototype. You can do this. Yet, as I said, you have some problem about the Reynolds number, so it's better. But for the hypergravity experiments, it becomes better. All right. Let's see. So it is kind of neat, right? You can control the body force to do some experiments. But there's some kind of drawback too. It's not easy to do. That's one thing. And what we did here is this. We used the UC Davis's centrifuge. I think it's about arm length of 9 meters. It's very long. And the bucket is about 80 centimeters. So this is the stuff. We put it in this bucket in here. And if you turn like this will be, this is like this. Okay? And then this box, specimen box is put it inside in this. Okay? And then this is the people we did this together. This is a PhD thesis by Maggie Exton. And what we did for this is originally you're gonna get this kind of conditions, reservoir, and I have a soil to examine. I have a G, NG, 40G for this case, right? And then suddenly I lift the scale. It's a dumb brake problem. That gives you a run up, right? Right. I think I forgot to erase P. Just ignore this P. There's no meaning for P, right? Oh, run up. P is here. Now I found out. So, and then you're gonna get the run up, and then you're gonna get the inundations for a while. And then I have a second gate open. And I have a subsequent drawdown. So I can examine for this behavior in the soil. Right? And for this, 1/40 model, make it very small, right? And if you have, but in the prototype, it's very, very large. I think it's equivalent to 20 meters for this case. But anyway, so we have to be very careful about for the small scale experiments. First of all, this guy has to be small. Sensor has to be small because model itself is pretty small, right? So as far as the pressure, pore pressure transducer is concerned, has to be very, very small. I also like to measure soil pressure itself. This is the problem. The soil pressure cannot be small. It's because of the soil medium is not really continuous. You have to have sufficient area to get the average value for the soil pressure. This is the smallest I can buy, 5 centimeters, but still big. 5 centimeters times 40. And it's very, very large in prototype. So, but I have to do this one. So I embedded those soil pressure in this. And then visually, I have to use the high-speed video. With small, you have to have high resolution. And then speeds up by 40 times. So you have to use the high-speed video to do this. And then what we did here is, oops, oh, this is okay. For the run-up case for this, I put the pore pressure transducers in here. This is the soil pressure gauge. And I put the impermeable layer in here. That's the things I'd like to try to find out what is going on. So you're gonna get the soil pressure gauge in here, soil pressure transducer in here. This is the pore water pressures. And I use the soil 40 times viscous fluids. So try to match the Tazagi number. And it may or may not, but we just try, right? I'm not claiming that I can make the exact similarity in the soil. And especially if I'm using the soil and for the fine sand, but if you make it the prototype scale, sand becomes common. That's the way it is. All right, let's see. I guess that's it for that. So you're talking about 50 centimeter long. If it's 40 times, it's 20 meter in prototype. Right? Okay. So I will show you, I hope I can show you some, where the heck is this? Some pictures for under 40G. This speed is really 10 meters per second. And this picture is taken in the 0.07 seconds. And you look like this is a real, right? Yeah. So this is the flow condition I generated in the centrifuge. Yeah, here you go. So this is some data for this. And you can see flow is from left to right, a different time. And then this is we repeated 2 cases. One case is with impermeable layer, other one is without. So it's pretty much same. The inundation depth, pretty much same for the velocity. It's slightly different arrival time. Not exactly why. It's supposed to be the same, right? Maybe some sort of glitches, but it's good enough, I guess. I don't think I need to worry about the arrival time. But what I'm saying that here is you're gonna get this kind of conditions. Velocity is 10 meters per second. Pressure here is about 30 kilopascals, which means about 3 meters, right? In the about 3 meters in the prototype. But in that centrifuge, it's gonna be like that. All right. All right. And then, so in the run-up case, there's a 2 stage for the run-up. Initially you have this kind of conditions coming out from here to here, run-up. Okay, and then feeding in the water in behind this, eventually it's gonna be highest value here. So it's gonna be backflow, actually not the backflow. The wave itself is gonna go in backward. So this is the gradual secondary inundations from the backup flows. Okay, okay, this is still run-up phase. For the run-up phase, it's a leading front and the backup flows. You're gonna get completely inundated for this. So for that, yeah. Was it nice? 1 second means about 40 seconds in the field. So this is the condition at here, the pore water pressure gauge. And if this quantity, delta is 83.4 kilopascals, and it's totally liquefied. Right. More or less it's liquefied, right? Liquefactions. So this is the raw data, and this is the water surface. And there's a two lines, which is pore water pressure, and also our excess total stress in here. So for this case, total stress and pore water pressure is constant. So delta is essentially equal to zeros. It's nothing happened for this case. This is the pressure at the bottom. I just want to repeat this one. Try to find the pressure at this bottom. This displacement is a run-up phase. So this dotted line is the water surface. There's two lines in here. One of those are pore water pressure, other one is total stress, total soil stress. It does not change any of the stuff for the run-up. Okay, so if you have impermeable layer, it does not change. Still same thing. Let me see it again. This is water surface. Those two lines represents the pore water pressure and the total soil pressure. So this quantity is equal to zero. Yeah, that means there is no change. That does not show instability. Okay? Because you have to go in up to 80 some kilopascal to make a total liquefactions. So it's sort of those two are boring. So this is not boring here. It's underneath of the impermeable layer. Right here, impermeable layer. So in this case, that the critical number is 13.7 kilopascals. Because that the elevation is higher. So for this, take a look at this. Pore water pressure is increasing faster than the total stress. Okay? So you're going to get the delta values like this. This means that somehow that the body effective, yeah, this is 9.15 kilopascals maximum. The critical number is 13.7, so it did not liquefy, but it's weakened underneath for this case. Okay. You understand this? Right underneath of this, you're gonna get the sudden downward stress that creates like this. But I will explain to you why this is so soon. This is more like a blast-related instability created in the soil, I think. You know, sudden loading, impulsive loading for this. And then we can try to find that later on this. So you're gonna get I wrote it down for this impulsive loading, but it's recovered quickly. Actually, I think I showed you this one, recovering very quickly part. This is the part I'm talking about, recovering very quickly for this. So that's what the quickly means. Take a look at this. This is 0 to 0.6 seconds. Right? And then we also talk about the soil stress reacts slower than the pore pressure. It must be caused by dislocation of the soil lattice. Some people call this the fabrics, right? Mm-hmm. So this is interesting. And then we're going to talk about second part of the rundown. you're gonna get a much larger loading, but much prolonged loading for this. You know, you understand that this is still run-up process, but this created by backup flow backup. Right? So for this, that's you just saw earlier in this portion only. That's what I showed to you earlier. We just wanted to make sure what I'm talking about here. This picture is right here. Right? Yeah, later on you have some data in here. I just plot the data. For this case, the maximum I get the 8.12 kilopascals. And then again, you have another difference between pore water pressure and the soil stress. And this is reduced rather gradually on the side of the impermeable layer. Behavior is different. Right? And this is again, it's not reaching the 13.7 kilopascals. So it's not a totally liquefied. Oh, maybe I should say that. For this criterion, it's not the liquefied. You do not know. But it's very close to. Let's see. So I'm talking about the substantial prolonged data for the secondary loading, this initial run-up, and the secondary loadings here. Okay? Let's see. And then we have on the bottom part, right here, you still have something going on. Okay, initial part for this, at bottom, there's almost none. Right? But secondary part in here is penetrating all the way to the bottom. This discrepancy is affected in the even bottom portions. So what is going on for this? So the first part here is, let's see, the first part here is, I think it's likely, the blast likely loading, you know, sort of a instantaneous instability is happening in the soil, but this part is much more prolonged. So it's a substantial prolonged data value. And I think this is created by something called the overpressures. But let me just talk about this one. During the impulsive increase, you know, you're going to get a temporal localized spike on data. So this is the same blast-induced soil instability. That's my interpretations. A similar one is happening later on also, but this is much more prolonged. It's I try to explain what is going on, and maybe I called overpressure phenomenon, or sometimes they call this equilibrium compaction. What I'm saying here is this is quite a bit used by geologists, and much larger scale. This is the one I try to explain. Maybe not this is the case, but you know, if you have an impermeable layer barrier here, take a look at these kilometers, 2 kilometers down here. This is the hydrostatic. This is the lithostatic by the soil stress. So because of the impermeable layer, this is shifted right here because of the pushing down on the soil structures in here. Right? So this is the one of the explanations, overbound loading. So it's very hard to reducing the expel the fluids from the pore space. That's conjecture. I should say this is my own explanations. They may or may not be right, but that's the way I have. So those are the run-up process. Okay, let's try to do drawdown process. Here it is. This is a more compact way to explain it. this is an isobaric line, isobaric bars for this, without any impermeable layer. It's pretty much horizontal. But that is not the case if you have an impermeable layer. Take a look at this portion. It's very high, strong gradient in the pore water pressure gradient at the edge of this, right? During the drawdown. So for this location, I also see some sort of a spots in here in the middle. Right? So during the drawdown, at this point, underneath of the impermeable layer, critical value of 13.7 kilopascals. Again, this is the water surface reduction. Straight line, solid line is pore water pressure, and this is the soil stress. So in between, difference will be delta. So this is the one I can get. So delta value maximum is 8.551 kilopascals at these locations. Again, it did not reach 13.7. It's about 60% critical values. But you have still weakening for these locations. And I just also wrote the pressure difference for this for the layer case and without layer case. Pressure, this is a pressure difference between the water surface and the pore water pressure case. It is different a little bit. You know, layer case has a greater delta P. But this is the part which I was interested in, delta value. For difference between pore water pressure and the soil stress. Okay. And I have this. This is at the bottom. Right here. At the bottom is not so much. It's pretty much the same on this. The difference is only a 4 kilopascals. So during the drawdown, I can only see that this portion has some kind of instability is creating. Well, I should say this creates a big difference with and without horizontal impermeable layer. That's how I should say this. So presence of the impermeable layer makes big difference in the soil behavior, right? Without any impermeable layer, it's just a you can sort of guess. During the drawdown, that might create instability. During the run-up, it may not. So with the impermeable layer, that creates soil can be very unstable for this area. And then, as I said, at the edge of that, this is quite important here, isn't it? You know, very strong pressure gradient on this. So this portion, soil becomes very unstable. Actually, that makes sense from the field observations. So this is a summary. We explore the mechanics of the soil response, tsunami-like rapid loading using this POTG centrifuge. And that gives you a realistic tsunami inundation process. Inundation height is 5 meters. This is 10 meters here. Oh, by the way, this place is about 19 meters H. It's quite a bit different. So this can be sort of explained if it's an impermeable layer. Underneath of this is unstable. And this can give you an explanation why this building failed during the run-up. So without it, I say that during the run-up, soil supposed to be stabilized. But that is not the case if you have an impermeable layer. Right? So, for the summary, if you have a run-up phase, sudden pressure rise creates the dislocation of soil grain. So this is blast-like instability, the very first part. And the secondary part is showing that the slower flooding, but still also create instability. And I call this is overpressure or this equilibrium compaction, which people talk Okay, some geologists are talking about much larger scale of phenomena. So that's my explanation for the run-up. For the drawdown phase, pore water pressure develop cause instability. And this is you reported earlier, but it's indeed if you have a drawdown that creates the gradient, pressure gradient becomes downward. That means pressure force becomes upward. But this experiment is the one which really presents actual field-like scale measurements for this. And then instability is created by if you have presence of the impermeable layer. So I think that the supporting structure for the basement and that the pavement becomes important for the soil response. And this is the results. I think this is it. This is my last slides. Quick talk. Thank you.
So with this, we open the floor for the Q&A session.
Questions?
Who has questions for Dr. Yan? Yes.
Patrick, I saw that video there significant past. So we saw that the scale is one of the faulty and the water is coming. I'm interested about the boundary.
Maybe I just. Let's see, that's my publications. I'm just gonna. This is the one you're talking about. Boundary effect. Okay. I should say, that's a good point, actually. I'd like to make a point also. Boundary effect is one thing, but take a look at this conditions going down like this. The bucket is moving like this. If the flow is moving in this direction, centrifugal force changes by the positions. That means you're going to create Coriolis terms. However, flow on this location, this direction does not create any. So, effect of the Coriolis force may be created by these portions. And then also, I try to make it as turbulent as possible. So I have some kind of bumps. I put some kind of bumps in there. And side boundary is, I don't think it's my concern because it's very fast. And the boundary layer on the side boundary boundary layer can be very thin. For this case, boundary layer squared nu t. Boundary layer thickness squared nu t. Oh, by the way, I have to say that. In order to make a nice similitude, I use viscous fluid in the soil. But if I use viscous fluid for this surface flow, then the Reynolds number becomes worse. So I use regular water for these portions. And only the fluid in the soil, I use the viscous fluid.
How much did you use?
Huh?
How much did you increase the viscosity?
40.
40.
40. 40.
For-
40.
40.
Mhm. 40 times.
More questions for Dr. Yan?
You get totally lost. But this is a nice toy, isn't it? Yeah. Next, I'm gonna try to put operate this condition manually. So send that the graduate student to centrifuge and the 40G.
To see how they perform.
Yeah.
So he did two experiments back to back. How much uncertainty, you're gonna get this, you're gonna get exactly the same result, there's gonna be variation.
I think I'm quite sure, oh, hold on,
What's the most?
hold on. The
uncertain-
variation is, okay, I can tell you that the source of error. In the centrifuge, I'm using like this one, right? The location of the sensor is a real problem. It's not easy. And also, how are you gonna saturate the soil is big uncertainties. We're using vacuum conditions. We use a CO2 gas, so it's gonna be resolved. It's lots of procedures, which is create a lot of uncertainty. Yes, this is not a totally, try to simulate exact conditions. However, that gives some kind of qualitative understandings. So that's the way it is for this. But one thing we're gonna use for the centrifuge here is if you know some kind of, reasonable conditions at hand, we can simulate the condition in the centrifuge numerically. That gives you some kind of validation for the numerical things. And those numerical models can be applied to the prototypes. So at least one way to give you some confidence for the application of the gravity numerical simulations. So I don't think that the centrifuge is really the solutions for that they try to find the real engineering answer quantitatively.
How many times did you repeat the same test?
Oh, I'm saying, no.
We can,
You see, well, you could, unless if somebody's gonna give me centrifuge, yes, I can.
yes.
But you have to prepare this one bucket.
Mhm.
It takes probably at least 1 week. Just prepare for this. And that's the drawback for the Nihiri, right? Or NIS. So you have to send the students there. But if you have apparatus in the backyard, I have no problem. I can spend about 5 years in these experiments. But for the shared facility, you only have a month and a half. And, if you do such kind of stuff, I'm quite sure something going wrong. So
To reproduce exactly the same characteristics and the position of the.
that's also very difficult. Yeah, because we positioning the sensor by using a stick. So
More questions?
You could do the same experiment, what kind of changes would you do?
what kind of changes I do? Let's see. Yeah, I have some. I forgot what I wanted to do. But maybe, yes, the critical. The location of the impermeable layer based on this is too deep. I wanted to put it a little bit shallow. Then it's gonna be liquid. I'm quite sure it's gonna be liquid. And then also, impermeable layer which I use for this is a plexiglass. And initially it wasn't. Initially I was trying to match the weight of the impermeable layer to the weight of the soil medium. That's a try to do it, which I think at the end, because it's easy. So those are two regrets, and it's very difficult going back to do the same thing. Because, I cannot operate this one by myself. I have to have several technicians. I do not have centrifuge in my backyard. But it's a neat toy. It's a very neat toy, you should have it.
Took the fluid velocity. You measure that with sensors or cannons.
Camera. Measure by camera. Yeah, it's not the fluid velocity, I will just measure the leading tip of the fluids. That's the leading velocity. So, in the tip, that's the speed. But can you must quite fast. In meter per second means The water is gonna be touching it up when they start to run. Because I cannot run at a 100-meter intensity.
More questions? I see people from geophysics, people, no, sorry, from geotechnical, from structures, from coastal. How do we put everything together and do a beautiful system to characterize all the behavior and all the interactions and having the scalability problems? So questions, how can we do that?
You can use this one for the SCAR experiments.
Actually, I have one question. So, about the scarring question. So, yeah, we know here with this significant capacity and scale, the vertical stress. So now we say the direct stress of the soil and the strength of the soil. This direction shares with not in the scale. So, how long the water this direction will give us some, for example.
As far as scaling is concerned, it's a three-dimensional scale. It's isotropic.
Yeah, the also scale. Share spread,
Share stress,
strength
straight.
of the soil is also the scale. And then we have the water in this direction. How about the water falls in this direction? Travels to their top. The resistance of the soil to the water is inevitable also.
We're talking about soil and flow of the movement of the soil particle
Yeah,
and the fluid flow.
yeah. And then we know that I don't know if I want to say see the prototype I have where, for example, really fall and the resistance of the soil in
This
this
is also soil.
and then in the centrifuge and the scale soil should be giving me growth, especially the spin this direction.
Okay, directions I do not know, but I'm gonna tell you, shear number, shear stress, the shear number is matches. So that means that they are, matches. So if you have a, if you're thinking about, fluid and if you're concerned about the interface between soil and the fluid, I can say that it's matches. It's very difficult to say this because it's not really, but it's not exactly, but I try to make a match for the shear number. But at the same time, I have to mention this. Soil itself, soil particle is not really scaled for this. As I said, soil particle for this is fine size. I don't even remember exactly what it is. I think it's about 200 0.2 millimeters. So that means if you multiply by 40, you can solve that. And then if you try to scale that the soil particle, then you have to consider other elements, other factors, which means that the cohesiveness, some chemical interactions kind of thing. So again, you simply cannot simulate the field conditions, but this will give you nice benchmark data to validate numerical model, which you can apply to the actual field condition. Because if you try to find this kind of stuff in the field, it's almost impossible, right? You cannot do some field. Or you might be able to put the forward of pressure in the sandy beach. You could, but then the loading is going to be different. I'm talking about loading for 3 or 4 meters deep, 10 meters under to the earth. If you're gonna place this forward pressure sensor in the swash zone, then the pressure difference is this much, right? So, and the velocity is much slower, so condition will be a bit much different.
for questions. Okay, so please help me appreciate the presence of the person with us, and during these days it has been amazing and a huge opportunity for us all to learn from him. So let's thank him for us.
Thank you. Yeah, I can
Thank you all
show
for
you.
coming.
This come out, yeah, it did come out.
Yeah,
Yes.
this is super cool. I want one of these cameras.
Oh, cameras. I gave it to Chris Higgins.
Oh, I need to call Chris and ask the camera. What is he using the cameras for?
Huh?
Is he using bridges?
I don't know, because I'm not gonna use it anymore, that's why. I shouldn't say that, people are listening. Oh, no. Somebody asking you questions. Yeah. Too bad, I'm sorry. Let's see if I can. No. I don't know. Stop share. Yeah, this is the way I'm supposed to do it. Oh, there's a 3 questions. Are you still there?
Angelica, can you unmute?
I cannot hear you. Hold on.
Yeah, I'm trying to see if Angelica can unmute herself.
Oh, okay.
I've given
Sorry
her,
about that. I didn't notice this.
I provided permissions for her to speak if she can unmute.
Yeah. Well, I think everybody's gone.
Uh, Angelica is here.
Angelica is there? Yeah. Angelica.
Hmm.
Sorry, I'm gonna just leave.
Yeah, sorry.
Thank you for doing this.
Yeah.
Appreciate it.
All right. All right.
Bye
Thanks,
bye.
everyone.